Modify the formula, right?
Yeah.
Okay. So, how do we modify this formula? C9. What do we do for each halogen?
Drop it out and then add 2 hydrogens.
Plus 2, right?
Yep.
What do we do for sulfur?
Just drop it.
Just drop it, no adding. What do we do for phosphorus? Okay, that might be confusing. You might be wondering, is that an O or a 0? Okay, do nothing. What about phosphorus?
Subtract 1.
Take away 1. Hydrogen, right?
Yep.
So 11 plus 2?
It's 13
And minus 1?
It would be 12.
That's your modified formula. Agreed?
CnH12.
For halogens, we add 1 hydrogen for each halogen. For group 6, just drop, don't add any hydrogens. For nitrogen, phosphorus, take away a hydrogen for each of them. You guys with me? Everyone okay? And then apply the formula. So what is IHD equal to? Half of, what's the saturated? What's
CnH20.
Do you all agree where this 20 is coming from? CnH2n plus 2 minus CnH12. So what is the IHD? C9 goes away, right? Cancel.
Minus 12
Equal.
is 8.
20 minus 12, what is that?
8.
And what is that divided by 2?
4.
IHD of 4.
Oh. Give
Are we
formula
okay?
about OS.
Yes? Okay.
Yep.
What about this one? Again, same thing, we have to modify the formula first using the rules here. So C12H, let's pause. What do we do for oxygens? There are 2 of them.
We give formula and drop OS.
Do we add any hydrogens for oxygens?
No.
What do we do for nitrogens? You take away a hydrogen. What do we do for halogens?
Add 1 with sisters.
But there are 2, so good. So how many hydrogens does that make?
18.
Do you all agree? Everyone okay?
Yep.
So that's your modified formula. And then IHD. Half of what is saturated with 12?
26.
Everybody okay with that?
Yes.
Minus C12H18. What is 26 minus 18?
8.
And what? I don't know. There's no rule that says it always has to be 4. That's just a coincidence that every example I'm coming up with is giving us an IHD of 4. But do you understand the process?
Yeah.
Is there a rule it has to be a whole number?
It does have to be a whole number, and it will be because you can't really have, that's why I need to balance out and make sure the hydrogens work out. So you can't have a fractional number. Because 1 IHD is 1 pi bond. You can't have half a pi bond. 1 IHD is 1 ring. Can't have half of a ring. So the answer is yes. It has to be an integer. Guys, does that sound okay? Is everybody following this? So this is actually a very helpful process when we use NMR to decide or figure out the compound structure. This is what I start with. My first step is always IHD because it really helps me narrow down my choices quite a bit. And we'll do that when we get to that part in chapter and we are solving NMR problems. We will come back to IHD. But if there's any step that's not clear, can you please make sure you ask so that it is clear when we get to that point? Clear?
Yeah.
Okay, then let's go ahead and start proton NMR spectroscopy. What are the different things? How do we use proton NMR spectroscopy to figure out the structure of a compound? Now, in proton NMR spectroscopy, which atom are we studying?
H plus.
Hydrogen, right? Not H plus, even though we are calling it proton because it's the nucleus that is interacting with the magnetic field, but it's really the atom that you're looking at.
Yes.
Not a chemical process. So, when we use proton NMR spectroscopy, we are studying the hydrogens in a molecule. There are 4 features to a proton NMR spectrum. Please remember, we don't call it a graph, it's a spectrum. Spectrum is singular, spectra is plural. There are 4 features to an NMR spectrum. First is number of signals, and we will go over each of them one at a time. So how do we figure out how many signals a compound should show, or so on and so forth? So we'll get to that. What this tells us, the number of signals equals number of types of hydrogens. Not all hydrogens are the same. So the number of signal tells us these many types of hydrogens, these many sets of hydrogens the molecule has. Next thing we look at is integration of every signal. Because this tells us, this gives us the number of H's for, maybe change that, responsible for each signal. So that's very useful information. The third thing I look for, actually, I'm going to write it as third, but that's probably the last thing I look for. But anyways, something called chemical shift. The symbol for chemical shift is lowercase delta. Let me write that again, didn't do a very good job. Chemical shift basically is telling us what is the chemical environment electronically, so electrons come in there, for hydrogens of each signal. And this is basically signal. This is basically the position of the signal on the spectrum. Although when I work through NMR, I think this is probably the last thing I go for, but we will discuss it third. And the last feature, which is one of the most important parts of proton NMR spectroscopy, is called multiplicity, also known as coupling. The magnetic field of one set of hydrogens can actually couple with the magnetic field of the neighboring set of hydrogens, which creates some predictable changes. And this, as I said, probably is one of the most important features of proton NMR spectrum, and it tells us how many hydrogens are on the adjacent. What does the word adjacent mean?
Next to.
Exactly. 3 sigma bonds away. So it's not telling us information about the hydrogens for the signal, it's actually telling us about neighboring. How many neighboring do I have? So it really helps a lot in figuring out the structure. So those are the 4 features of a proton NMR spectrum. You guys with me?
Yep.
Questions? We will of course hit on each of them one at a time. Okay, then let's start with number 1, number of signals. Number of signals tells us the types, how many types of hydrogens a molecule has. So, equivalent hydrogens, or hydrogens that are absolutely identical to each other, we call them equivalent hydrogens, and they give us one signal. Okay, so, and we look at some options here. Are you guys with me so far? Mm-hmm. Okay, so let's start with something small. and then we will slowly build on that. How many, methane, CH4? How many hydrogens does methane have?
4.
And if you draw out its structure, are these 4 hydrogens identical to each other, or are they different from each other?
Identical.
Do you guys agree?
Yep.
So the 4 hydrogens in methane, they are all equivalent to each other, which means 1 NMR signal. Make sense?
Mm-hmm.
Everybody okay?
Yep.
Everyone convinced? I'm not seeing that enthusiasm in some of the faces. Do you guys agree or you guys don't agree? Agree? Okay.
Yeah, that's okay. Yeah.
Then let's go to the next option. Ethane. What's the total number of hydrogens in ethane?
6.
Right?
Yep.
What's the structure? Agreed? Okay.
Do you want that out? Or you?
Please, thank you, Mark. Thank you. It is very annoying. Appreciate it. So, let's pause. I want to ask you about these 3 hydrogens only. Are they identical to each other or not identical to each other?
Identical.
Do you guys agree?
Yeah.
These 3 guys, totally identical?
Yeah.
There's a quick check, by the way. If you're not ever sure, if you're looking at a molecule and you're not 100% sure, there is a quick way to figure that out. Do you want to learn that quick way?
Yes.
And you can just do it in your head. You don't have to write it out. You can do it in your head. One quick way is, and I'm only focusing on those 3 right now. One quick way is, okay, what if I replace one of those with anything else? Let's say Cl. I'm just picking something. It can be anything. Let's say, if I replace those, one of them, I'm replacing this with Cl. Or I replace the other with Cl. Are these the same or different? What would you call this guy? Name. What is the name of this molecule?
See,
This should not take this long. This should be a 30.
1-chloroethylene.
Do we need to say for ethane, because either way it is, it's going to be 1
1 chloroethylene.
chloroethane?
Yep.
But even if you call it 1 chloroethane, I'm happy with that also. What would be the name of this guy? Same thing, because they're the same.
Chloroethane.
What if I replace the other with chlorine? What would you
Still-
call it?
Still
So
chloroethylene.
do you agree that these 3 are the same?
Yep.
That is a quick check that, oh, that means these 3 hydrogens are equivalent. They're identical to each other. We call them, here are 3 terms we are going to introduce. These hydrogens are therefore called homotopic hydrogens. They are absolutely identical to each other. You guys with me?
Yeah.
Okay, what about these 3? Are they identical to each other? Again, you can do a quick check, mental check, replace each one at a time with something, Cl, Br, something easy.
Yep, these are identical.
Would they give us the same
Yes.
result? Everybody agrees?
Yep.
So these are homotopic with each other. These are also homotopic with respect to each other. You guys with me?
Yep.
Yes?
Yeah.
Yes.
What about red and blue?
No.
Yeah.
Are they identical?
Yes.
Absolutely. So in this example, all 6 hydrogens, all of them are homotopic with each other. No matter which hydrogen you replace with Cl or Br or I, you will end up with the exact same compound. Do you guys agree? So how many NMR, proton NMR signals should ethane show us?
1.
1, because they're all identical. Is that okay?
Yeah.
Cool. Then what about propane? What about propane? Let's extend the same concept here. how many proton NMR signals should propane show us? Well, that depends on how many types of hydrogens it has. Now, do you guys agree that there are 3 hydrogens here?
Yep.
Are these identical?
Yes.
Are they homotopic?
Yes.
Okay, good. There are 3 hydrogens here, do you guys agree?
Yeah.
Are they identical to each other?
Yes.
Are they homotopic with each other? What about the blue and the red?
No, because the CH2 on the top.
So, okay, let's do a quick check. Let's say I replace one of these with Cl. What would you call it?
Chloropropane.
Do you guys agree? What if I replace one of these with chlorine? Again,
Chloro-
there's
Chloropropane.
one chloropropane, right?
Yeah.
So are they identical?
Yeah.
Absolutely they are. Because why? There's a quick check for that too. What does this
Oh.
molecule have?
Plane of symmetry.
Plane of symmetry. Because of that plane of symmetry, this is identical to that. Everyone with me?
Yeah.
So, would you be okay if I said these three, so all 6 of them are homotopic,
Mm-hmm.
Yeah.
meaning they will give us one signal.
Yeah.
Okay. Are there other hydrogens in this molecule?
Yep.
Yeah.
Where?
On the second carbon.
Right?
Yeah.
Are these, again, hear me out, are they identical with each other?
Yes.
Yep.
Are you sure?
Symmetrical? I don't know.
Okay?
Yeah.
But are they identical to the red?
No.
No.
Are they identical to the blue?
No.
No.
So this molecule, how many sets of hydrogens does it have? 2.
2 sets.
So how many proton signals should it
2.
show us?
2 signals.
You guys with me?
Yep.
Everybody okay?
So,
Yes?
so
Yes.
2 because homotopic and those.
Exactly. These are homotopic with each other.
Yeah, but there's 2 different homotopic.
Yes, exactly. So that's one set, this is one set. Everybody okay? Okay, let's do butane. Let's go to the next alkane. How many types of hydrogen do you think this molecule has? 2? Which 2? Do you agree? 1? Same?
Yeah.
Yeah.
Everyone agrees?
Yeah.
Yep.
Now, what is the relationship between these 3 hydrogens?
Identical.
And in other words, homotopic. How about these 3? How about these 3 and these 3 compared
Homotopic.
to each other? Homotopic. Everybody with me?
Yeah.
Yep.
Cool. What's the second type of hydrogens in this molecule?
It's 2, yeah.
C2 and C3.
Agreed?
Yes.
Now, what is the relationship between the 4?
Homotopic.
They're homotopic? Agreed?
Yeah.
The 4 blues. Right now I'm only focusing
yeah.
on the blues. Do you
Yeah.
agree?
Yes, yes.
Now please pause. What about this blue and that red? How are these related to each other? So, there's another term I want to introduce to you. By the way, what's the hybridization state of that carbon? sp3. So if I wanted to draw it a little bit more with a 3-dimensional perspective, would this be appropriate?
Yes.
Okay, let's do the same check. Let's replace one with Cl or the other with Cl and let's see what we get. So if I replace this with Cl,
It would be chlorobutane.
yes, but 3-dimensional perspective here. What if I replace that with Cl? Now, are they identical? No. What are they? What's the relationship between these 2 structures?
Diastereomers?
No.
they're enantiomers.
Enantiomers. Enantiomers. Do you guys agree? Do you guys see how that's different from here? That's different from those CH3s because no matter which you replace, there is no stereo center. But here now we do have a stereo center right there and right there. Isn't that right? What's the relationship between these 2? These are enantiomers of each other. So, Absolutely, those two hydrogens are identical, but they're not homotopic. Those hydrogens are called, meaning they are in enantiomeric environments relative to each other, meaning that if this gives us one mirror image, that's going to give us a non-superimposable mirror image. So they are not homotopic, they are enantiotopic. However, from NMR's point of view, they only give one signal. In proton NMR, that only gives one signal, so it doesn't really matter. But they're not technically not homotopic, they're enantiotopic. Are you guys with me? Yes? Questions? No. Okay. Let's look at another example.
So the whole,
Oops,
the
sorry.
whole molecule will give two signals then? Because
Yes,
okay.
yes.
Just wanna make sure.
Enantiotopic gives one signal, and yes, you're right, the CH3s will give a second signal. Absolutely. Okay. Okay, let's say this is the molecule. Question is, how many NMRs, proton NMR signals should this guy show? Okay. So first our job is to figure out how many types of hydrogens does that molecule have? What do you guys think?
Three.
Sure.
Four types.
Yeah, four.
Everybody okay?
Yes.
Which four? Do you all agree that these are one?
Yeah.
Yeah.
Can I just call it A?
Yeah. Sure.
Is this the same as that?
Yeah.
Is this CH3
Not anymore.
the same as that CH3?
Yeah.
No, they're
No.
completely different.
How?
Good,
No
great
symmetry.
question. Let's figure it out. What if I replace one of those with a Cl
Oh.
versus I replace one of those with a Cl? Do I get the same compound?
No.
Is this the same as that?
No.
No.
Is this the same as that?
No.
Good. Do you guys see? That's 1,2-dichlorobutane. This is 1,3-dichlorobutane. They're structural isomers. They're not the same. So the point is this CH3 identical to that CH3?
No.
Please look at the chemical environments. The chemical environments are completely different. This CH3 is 1 carbon away from Cl, whereas that CH3 is 2 carbons away from Cl. They're chemically in different places. You guys with me?
Mm-hmm.
So do you agree that this should give us one signal and this should give us a separate signal?
Yeah.
Where is your third?
CH2.
Those two?
Yeah.
Can I take that last?
Sure.
Where's the rest one?
Let's see how,
That one. It's unique. There's nobody like it. Agreed?
Yeah.
Sure.
Now I want to pause on these. There are two hydrogens, absolutely. That's a methylene group. Two hydrogens, but are they identical?
Yeah,
They're not.
they're different.
They're different. How so? So, let's bring some three-dimensional perspective to this discussion. Is there a stereo center in this molecule to start with?
Yeah.
Where?
Yep.
C, or the
The
one
CL.
attached to C.
So I am randomly, why are you choosing this? Just cause. You could have chosen the other. You'll come up with the same conclusion. I'm starting with this enantiomer. Agreed?
Sure.
Now, there are two hydrogens on that methylene carbon. One is on a wedge, the other is on a dash. Yes?
Mm-hmm.
When this hydrogen looks around itself, what does it see?
CL.
Also on a wedge as that.
CL.
Yes? When this hydrogen looks around itself, where is chlorine relative to that? On the other side.
To the right.
They are totally different. Chemical environments are not the same. They will give us different signals, at least expected to give us different signals. What's the term used? Let me tell you, let's go over that. Okay, what do we call them? No, sorry? No, not really, because that's good. Let's discuss that. So I'm starting with this as my base. I'm going to replace one with Cl versus the other with Cl. What is the relationship between these two? They're diastereomers. Configuration fixed, configuration switched. If some configurations are fixed but others are changed, then you have diastereomers. These are diastereomers of each other. Do you all agree?
Yeah.
So what do you think we call those hydrogens? Perfect.
Diastereotopic.
Perfect. Diastereotopic hydrogens are not in the same chemical environments. They are not expected to give the same signals. They will give you two signals. Each hydrogen is in a different chemical environment. And in fact, if you drew out the Newman projection, if you drew a Newman projection along that bond, it becomes really clear that, yeah, they're not in the same chemical environment. So if that's my front carbon, chlorine is here, hydrogen, methyl, sorry, and then I'm seeing methyl, hydrogen. So here is, fine. I'm comparing this hydrogen to that hydrogen. Notice the blue and red are not in the same chemical environment. The blue sees chlorine close to it, hydrogen does not. So that is a clear indication that, yep, NMR, they're not NMR equivalent. They're not in the same chemical environment, which means we can expect them to give us two different signals. Does that make sense, everybody? So does everybody understand what are homotopic hydrogens, what are enantiotopic hydrogens, and what are diastereotopic hydrogens?
Yeah.
Cool. Oh, shoot. So, I forgot. This was the original question, though. How many signals should we see? 5. So we have A, we have B. These are homotopic with each other. That's unique. And then B, because those are diastereotopic. Is there a quick way to figure out whether hydrogens are homotopic or diastereotopic or enantiotopic without doing any of this replacing and all of that stuff? The answer is yes, there is. Here is the hint. CH3s, hydrogens on a methyl group, will always be homotopic. Because there's no stereo center being generated by replacing them with something. Period. It's the methylene that you have to be careful of. This is, by the way, this is methyl group, we all know that, right? Everybody knows methyl group?
Yeah.
This is called a methylene group. It's a common name, it's not an IUPAC name. So if somebody says methylene group, they're talking about a CH2. Here you have to be careful because these two hydrogens will be enantiotopic with each other, if no prior stereocenter in the molecule. But if there is a prior stereocenter in the molecule, then these will be diastereotopic.
Doesn't matter if it's a long ways away.
No, it doesn't matter, because you'll end up creating a diastereomer no matter what. Absolutely, doesn't matter. If there is a prior stereocenter in the molecule, then the new one is going to create diastereomers. So those are diastereotopic. In homotopic are equivalent, meaning one signal. Enantiotopic are NMR equivalent, meaning one signal. Diastereotopic hydrogens are NMR non-equivalent, which means they are expected to give separate signals. Yes? Good.
What do you mean by no prior stereotype?
The two examples that we saw, there is no stereo center in this molecule. That is why these are enantiotropic. Because there is no stereo center already. We good? But the other example we saw, notice there is a stereo center. So therefore these are diastereotropic. Does that make sense?
So whenever we have a stereo center,
Exactly.
that means
The CH2s, only the CH2s though, methylene. Does that make sense, Carrie? So by the prior, I mean that it already is there. There is no prior stereo center, but there is a prior stereo center. We good?
And what
Yes.
Eric asked is if it's longer, it doesn't matter.
Doesn't matter.
Mhm.
Doesn't matter. So those are the three kinds of hydrogens depending on where they are, what they are. By the way, since I already started this, let me finish it. That's a methyl, this is a methylene, and another term to get familiar with is this is a methine group. Is it YNE or INE? I think can't be YNE. I think it has to be INE. So when somebody says, oh, where's that methine group? They're talking about a carbon with one hydrogen on it, an sp3 hybridized. These are sp3 terminologies. Are you guys with me? So ready to do more examples? Okay. Please,
Sure.
can you, yeah, I know, I could feel that suppressed enthusiasm running through this room right now. Please, can you take one and pass?
I love
Why do I have so many? I don't think I gave somebody enough.
I'm in pain. This is a
I
lot.
hear you. So much.
Like, I'm confused. I thought I got it. And then she just started talking. I'm so tired. I can't believe I got 14. I thought I was gonna
Guys,
get
can we do this? We don't
a
have
really
too much
bad
time.
score.
Did everybody get one? Then why do I have so many? I know Vivian's not here, but still I have too many. Okay, let's look at the first question. By the way, we'll go through this stage by stage. So right now, all our job is to look at these molecules in the next 2 or 3 pages and decide how many NMR signals would they, proton NMR, only proton right now, signals would they create. Please go ahead, try it out, talk to each other. And I will draw them here so we can put the answers on the board for everybody. But in the meantime, please work it out with each other. The only thing we are focusing on right now is number of H signals, H NMR signals.
Do you have a pencil or
Pencil?
a sharpener? This one feels
Yes?
So if there are two antiatomic, are they the same group?
Does it have less?
Same group
Yes.
on two separate atoms?
As long as there's symmetry.
Symmetry of that.
Symmetry is necessary. I didn't realize I had so many. Ugh. then I'm going to skip a few because we can't. The keys are on canvas, guys, but we can't really go through all of them together in the class. That looks interesting. This looks interesting.
I'm gonna say this one's got two. I don't know. What do you think?
Oh, Wednesday.
For the first one, I said two.
Hmm?
For the first one, I said there's two signals.
I said one. But you're probably one.
I think there is one. Yeah.
I think there's one.
This one.
What about the third one?
No, I think there's two. Because the reason why I think there's two is because this one has an H right here, right? There's an H.
No.
Yes, there is. This one is
How
C.
could it have H? It's got 4 bonds. It can't have more than 4.
This one doesn't have. No, I'm talking about this.
Yeah,
This-
that's a C.
Oh yeah.
Count all hydrogen.
You're
All
thinking
hydrogen.
these.
All hydrogen. Everybody. The answer
can't
is
believe-
yes, all hydrogens. They'll have their own signal. Exactly. So the point is, I'm assuming you're talking about this, right? So the point is this hydrogen which is on an oxygen the same as this hydrogen that's on a carbon? No. So it'll have its own signal. But we look at all hydrogens. Absolutely.
So do you treat it like a carbon? Oxygen like a carbon, but it just has its own signal?
Yes.
Okay.
If that's how you're able to better understand, then yeah, sure, absolutely. You're looking at every hydrogen in the molecule. And there are many more. I think we might have to pause here because we won't have time to go through everything, but please do work on it. Okay. So all we are doing right now, guys, you are telling me how many proton signals should these compounds give us. With me? Can we go start with the first?
Yeah,
What? How many?
One.
Do you all
one because
agree?
it has CH3s on it.
All CH3s are completely homotopy with each other.
Yep,
Everyone okay?
yep.
How about this guy? 3? Did I hear 3? So do you agree that those are one set?
Yeah,
What kind of hydrogens are these?
The
Different, but what? Different than A.
Oh, you mean,
So these are homotopic, right?
with each other. Oh,
With each other. Yes, these are homotopic with each other.
I was saying B.
What about B?
Same.
enantiotopic?
They
With-
are
with themselves.
enantiotopic. CH2s, and there is no stereo center. So then the CH2s are
Oh,
enantiotopic.
Mhm.
But do enantiotopic give one signal or two signals in
Two.
NMR? Just one.
Just one? Oh,
Diastereotopic are expected to give two.
oh, that's right.
And what about this? This CH3, homotopic, enantiotopic, diastereotopic.
Homo.
How about that?
Same.
How
Homo.
about that?
Homo.
How about the 9 of them?
Homo.
They're all homotopic because you can rotate about the single bond. You guys with me? So how many total signals? 3 signals?
3.
Everybody on the same page? Let's start here. How many signals?
3.
Are you sure?
I said 2.
Are you sure?
I said 2. I don't know.
Are you sure?
I'm not very sure.
Let's try something else then.
Well.
How many? Did I hear 1? Did you say
Oh,
1?
what about the top one? 3, 4?
Did you say 4?
4.
4.
I forgot the top one.
4. Of course, there is symmetry. Do you all agree that there is symmetry?
Yeah.
Which means this side is identical to that side, right? So do you agree that this is one set?
Yep.
Same. Do you agree that the CH2s that are enantiotopic, because there's no stereo center, because there's symmetry. So these are enantiotopic, but they are both same. Agree? Yes?
Yeah.
Do you agree this methyl is totally unique?
Yes.
But then where's the 4th?
The H.
The one hydrogen.
Let's not forget that. Matters. 4 signals. Are we good? How about this guy? How many signals total? Again, there's symmetry here.
Okay.
How many signals? Three. A, which is the same, right?
Yep.
B, the same, they're enantiotropic, so they give one signal in NMR, and these are also identical. Okay, next one, how many? 5. Do you all agree? Actually, not 5. 6.
Yes.
You guys ready? Let's start with this. Are these 3 hydrogens homotropic with each other?
With each other.
Yep.
How about those CH3s? Are they the same?
No.
No. And can we just get this out of the way also that it's going to be different because it's on an oxygen, not a carbon? Agreed?
Yep.
Where is D? Right there? So where is E and F?
On the top.
Because these are, what kind of hydrogens are those? Why?
There's a
Diastereophos-
Center. There's a stereo center, so at least our expectation is, and I keep saying this expected, because sometimes instrument, what you get, the result may not match, but our expectation is that they are diastereotopic, so they should give us separate signals. You all okay?
Yeah.
Diastereotopic, separate signals. Homotopic and enantiotopic, same signal. Okay, what about this guy? How many do we expect? 4 I heard. A, B, C, and the T-butyl is identical. T-butyl will always have identical because you can rotate about the bond, single bond. We all good? Yes, Carrie?
I'm sorry, could you please repeat what you said about how the hydrogens are diastereotopic?
Those ones?
Yeah. Is it because when you do the test on it?
Yes.
It's different?
Exactly. And how do I know? What is the quick check?
The stereo center.
There's a
That's
stereo
Yeah,
center
there's a
in the
stereo center.
molecule, so those become diastereo. The prior stereo center that we were talking about.
Okay, so if there's a stereo center, there's a diastereotopic.
Then CH2 is diastereotopic. Exactly. Are we all okay then? Let's go here, guys. Let's go do this really, really quickly. How many do we expect?
3.
Everybody okay? A, those are enantiotopic because there is no stereo center. So those are enantiotopic. These are homotopic. Oops, sorry. C. Everybody okay? Questions? Okay. How about this one? And that's a little tricky. That's this one, with the double bond.
Yeah.
So how many proton NMR signals should we expect to see?
wait, where am I?
So let's start with simpler things. Do you guys agree that that's going to be on its own?
Yep.
Okay. What kind of hydrogens are those?
Enantiotopic.
Because there's no stereo center, so these are enantiotopic. Agreed? So should they give us the same signal or different signals?
Same.
We good? Then where are other hydrogens? Do you agree there's a hydrogen here?
Yep.
Is there any other hydrogen like that?
No.
That's unique on its own.
Yeah.
Agreed?
Yes.
So where's the tricky part?
The double bond at the end.
Is this hydrogen? And please look at the whole molecule.
Yes.
Same as this hydrogen.
No.
No.
Oh.
What's their relationship?
They're
That's diastereotopic.
They're diastereotropic hydrogens. That is cis with respect to the hydrogen. This is trans with respect to the hydrogen. Or this is cis with respect to the CH2 part. That's trans with, so the point is there's a cis-trans relationship between them. Is everybody seeing that?
Yeah.
They're diastereotopic. They will give us different signals.
No, so it doesn't matter that there's no center, stereo center.
Double bond serves as a stereo center because double bond can have cis or trans, and that's basically a stereoisomer.
I'm confused.
Okay,
why
but do you
don't
agree that that environment is not the same as this environment?
Yeah.
Which basically tells us their signals are different. They will not give us the same signals. One is a cis isomer, the other is a trans isomer. And the relationship between cis and trans is that of diastereomers. You guys with me? Yes?
Oh, to figure out if it was cis or trans,
Yeah.
it was just the adjacent hydrogen that we were.
Okay. Let's do the check again. If I replace that hydrogen with Cl, okay? The red hydrogen with Cl. Versus I replace the black hydrogen with Cl. What's the relationship between these two?
Cis and trans.
Do you guys agree? That's a cis isomer, that's a trans isomer. And what do we call cis trans isomers? What kind of isomers are they? They're diastereomers. So which means that these hydrogens are diastereotopic. Are you all seeing that?
Yeah.
Is everybody seeing it?
Like, yeah, service.
Okay, let's go to the next one. How many do we expect? Do you agree A? Yes? Do you agree B?
Mm-hmm.
How about C?
Yeah.
How about D?
Uh-huh.
And
Yep.
5? Did I miss any?
No, yeah, you got it, you got it.
Everybody okay? Next one, how many? Guys, are we okay with this? Clear? Everyone is okay with this example? Yeah?
Yeah.
Okay, next one. What do you guys think? How many? I'm full of good questions. I'm looking for good answers. Okay, do you agree there's a hydrogen here
Yes.
and it's unique?
Yeah.
There's no other hydrogen like it? Everybody? Okay. What about those two hydrogens? Can double bond have excuse me, I misspoke. Can a triple bond have cis trans?
Yeah. I mean, like on a triple bond. But, I mean,
No,
it can't.
can
No,
a triple
right.
bond be cis
No,
trans?
no.
Can a triple bond have stereoisomers? So can that, basically the point is there a stereo center in this molecule already?
No.
No. So what does that make those two hydrogens right there? And
Enantiotopics.
they are NMR. And they are enantiotopic hydrogens are NMR equivalent or not equivalent?
Equivalent.
One second. You guys with me? Okay. Where else? What else?
There's two more. The one of them the end of the thing and then one of the middle thing.
So do you guys agree that these three hydrogens are equivalent homotopic with those three?
Yeah.
Yep.
Right?
Uh-huh.
And then where's the fourth?
One of them.
Oh.
Yeah.
Isopropyl group.
Splendid.
Everybody okay? 4 signals total? Okay, next one. What do you think? How many signals for the next one? Come on, guys. How many signals? 2. Absolutely, just 2. A, and all 9 of them are equivalent. T-butyl, the 3 methyls on a T-butyl are identical. 2 signals. Everybody okay?
Yeah.
How many here? Can I erase these 2? Is that okay?
Yeah.
Next one. What do you say?
Wouldn't it be?
You said 3?
I say 2,
You said 2?
but I might be wrong.
Again, we got to look at the chemical environment. Do you guys agree that these hydrogens are identical to each other?
Yeah.
Yeah.
Because they are both next to the Cl.
Yeah.
Yeah.
And plus, notice there's a plane of symmetry also.
Mm-hmm.
Do you agree that these two hydrogens are identical to each other as well,
Yeah.
but not to the red?
Yeah.
Yes.
Yes.
Yeah. 3.
Then what about that guy?
It's its own.
Is that identical to the red or the blue, or is its
It's
own?
on
It's
Only its own.
Yeah.
So it's 3 signals.
3 signals.
Yeah.
There's a plane of symmetry that's going right through the chlorine and the CH, which means this is unique. But this side is the same as that side. 3 signals. Everybody okay? Okay, please go ahead. Let's do this quickly now. With this idea, can you please tell me how many signals for the 6 benzene isomers drawn here on the board? What did I do?
Oh, I thought you said bromine. I thought you said bromine.
Did I say bromine? I
You said
may have.
benzene. You said benzene. I just thought of you said bromine for a second.
Maybe half of me is right and half of you is right. Let's just meet in the middle. We're both okay. But let's do the same thing, guys. What do you think? How many signals? 2. Are you sure? Look
4.
very carefully. 4. Chlorine is not the same as bromine.
Yeah.
Chlorine and bromine are different things. So do you think, guys, this hydrogen is the same as that hydrogen?
Yeah.
Yeah, it is the same?
No.
Carter,
Oh no.
that H is close to chlorine.
Oh no.
This H is close to bromine.
No, it's
Are they going to be the same or not?
No.
Absolutely. Exactly. What about the 2 center ones?
No.
No. 4 signals total. Absolutely right. Let's call this A, let's call this B, let's call this C, let's call this D. 4 signals. They're all different. Everyone okay?
Yeah.
Because there's no plane of symmetry, notice. There's no symmetry. Okay, what about this though? What if I make them the same?
2.
Then there are 2, because there's a plane of symmetry right there, so meaning these are the same and these are the same.
Yeah.
Agreed? How about the next one, guys? Bless you. How about the next one? How many should we see?
4. Yeah.
3,
4? 4 again?
Yeah.
No.
A, B, C, D?
Yeah.
Yeah.
There's no symmetry. Yes? What about this guy? I heard 3.
Symmetry.
Because there's a symmetry. Where is the symmetry going through? Plane of symmetry going through? Right? So that means this is unique, but then these are the same, and this is unique. 3 signals. Everybody okay?
Yeah.
How many for the next one? Sorry, could you please say that again? I lost my focus for a second. Are you
2.
sure?
I said 2.
There's a plane of symmetry there. Just because chlorine, bromine are definitely different, no doubt. But the molecule does have a plane of symmetry. Where is the plane of symmetry? It's cutting bromine in half, carbon in half, and chlorine in half. The plane of symmetry can go through bonds, can go through atoms, anything, as long as you have 2 identical halves. So, these are identical because they're both next to bromine, right? And these are identical because they're both next to chlorine. 2. How about the last one?
1.
Louder?
1 signal.
1 signal. There are 2 planes of symmetry. There's one here, there's one there, which means these are all identical to each other. Just 1 signal. Are you all seeing this? Does everybody understand what are homotopic hydrogens, anechotopic hydrogens, and diastereotopic hydrogens? Because the first thing we do when you're interpreting a proton NMR spectrum is trying to figure out how many signals the molecule has, because that tells us how many types of hydrogens we should think about. You guys, questions? Anything? Yes.
If I stuck my hand in an NMR machine, would I get cancer?
Good, great question. Ours, no, because ours is a very weak, puny instrument, which I wish we could replace, but we don't have the funds. But if you were to go to UW or any big university, their NMR instruments are cooled with liquid nitrogen, because you need to really do that. And it's in a lead protected room where you should not take your credit cards and your keys. You should leave those outside. So in that case, yeah. So just don't do it. But ours is very, very weak. Ours is 60 megahertz instrument. That's the strength of the magnet that we have is 60 megahertz. Typically, universities use 500 megahertz to 700 megahertz instruments. I would love to get a hand, but yeah. But so the answer, I hope I answered your question.
Yes, you did. Thank you.
We'll talk to Bill Gates.
First.
We'll talk to Bill Gates.
Some do, yeah. It's all about funding, right? It's all about how much research money schools are bringing, and then, yeah, absolutely.
I think I told them I give you one for Christmas.
Say again?
I told him they gave you one for Christmas, because he was talking about how many they have at UW.
Who said that?
Ricky.
Ricky said that? I would love it if Ricky will be back. Tell him he'll be my favoriteest person forever and ever if he can get us. But you know what? We are not capable of actually. Okay, I take that back. Our facilities are not capable of handling that instrument. That instrument needs its own room, its own person to take care of, kind of thing, on a daily basis. So maybe not. Tell Ricky he's still the same in my books. How's he doing, by the way? How's his daughter treating him?
He's delighted.
Is he sleeping? I thought he said that his daughter is actually sleeping
Yeah,
through the night.
he said she's sleeping well.
Questions, guys? Okay, then let's go to the second point. Can somebody remind me what's the second feature of an NMR spectrum? Louder? Integration.
Integration.
Okay. Integration is defined as, what integration really means, it's the area under each signal. Now, that's really what it means. So basically, please just try and understand this. Let's say I'm looking at a proton NMR spectrum. I see one signal and I see another signal, blah, blah, blah. These are peaks, by the way, because they go up. Unlike IR, where signals go down, these go up. So integration is measuring this area under the signals. That's integration. And the area under the signals is proportional to, meaning integration is proportional to the number of hydrogens for each signal. So more hydrogens causing a signal, more area, less hydrogens causing the signal, smaller area. Make sense, everybody?
Yeah.
Yeah? So let's say, and I'm just taking a random example here. Let's say the blue was 3 times the red, the area. So the blue area compared to the red area is a ratio of 3:1. What that basically tells us is that therefore the number of hydrogens causing this signal is 3 times as many as the number of hydrogens causing that signal. So it's a ratio really. Integration is a ratio which gives us the ratio of H's for each signal. So I mean it could be just randomly that okay, maybe this is a CH3 group and so that's 3 and this is a methine group, so that's 1, sure. Or it could be that there are 2 of them versus 2 of them, as long as the ratio is 3:1.
So it's always 3 to 1.
In this example, where I'm hypothetically saying that that's 3:1, so then it'll be 3:1. You guys okay with me?
Are they all, is it gonna be all whole numbers?
Yes, because you're dealing with ratios, so you want whole numbers. If it comes out to 2.89, just round it to 3, because it's better to work with that. Is everybody following that? So, yes, go ahead.
So you can just determine those ratios just by looking at.
Exactly. And we look at actual spectra also. Once we are done with understanding the different parts of the proton NMR spectrum, we will analyze actual spectra. And then, yeah, we will. So, for example, the first one had only one signal. Can you tell me how many signals did this guy have? How many signals did we say this molecule should show us? I'm sorry? 3. Isn't it 3?
Yeah.
Right? Which 3 again, just to remind everybody? Do you agree those are identical?
Yeah.
These are identical. Enantiotopic, they're enantiotopic, but NMR identical. And these are homotopic, agree?
Yeah.
So now, what about the integration? So A to B to C. How many hydrogens are causing signal A? Total of?
9.
How about signal B? How about signal C?
3.
Oopsie. 3, right?
Yeah.
Can we reduce this further? 9 to 3.
Wait, where
Yes.
did you get the 3 from?
Oh no.
3 hydrogens, right?
Oh, yeah, my
1,
bad.
2, 3.
I'm sorry, my bad.
Oh
Can we
yes.
take the numbers 9, 2, and
No.
3 and reduce them to a smaller ratio?
No.
So that is the integration ratio that you will see for the signal. So again, I'm not going to sketch out here because we're not talking about chemical shifts just yet. The point is, we will see 3 signals. Okay, fine, I'll stretch it out. Okay, just I'm hypothetically creating something here, which may or may not be this correct, but just to present a point. Can you tell me 3 signals, because we expect 3 signals? Knowing the ratio 9 to 2 to 3, can you tell me which of these signals is A, B, or C?
Middle is A.
Middle is A, right? Do you all agree?
Yeah.
Then where's B?
Right.
Do you all agree?
Yes.
I mean left.
But I heard that. But does everybody agree?
Yeah.
All we are doing is we are looking at basically, okay, the integration of this versus this versus this, and we are noticing, okay, that's the biggest signal, smallest signal, blah, blah, blah.
Yep.
Everybody okay?
Yeah.
That's integration basically. So let's do a couple more examples to understand yes.
So if you looked at just an NMR thing, you wouldn't be able to pick out which H's are what. You'd only get the ratio of unknown H's. Is that, or like if I'm looking at the graph, I don't know where
Don't call
A
it a
is.
graph, please.
Say again?
Don't call
Oh,
it a
right,
graph.
spectrum, you're right.
Thank you.
So if you're looking at the spectrum and you just see those big spikes and you
Yeah.
don't see the molecule and you're trying
Yeah.
to find what the molecule is, do you know where those H's are? Like what H's they are?
I hear your question. I'm just trying to phrase the answer in my head first. Yes and no. No, because not with the technique, the level of the technique we are studying, we can't just use this information and we need to collect all the 4 things and put it all together. And it's like solving a puzzle. You get some clues here, some clues here, some clues here, then you put it together and come up with an answer.
Right.
Then I said yes, because the amount of NMR we are studying right now in this course, at this level, is probably only 20% of NMR that actually exists. What we are studying is a very simple one-dimensional NMR. NMR can be 2-dimensional. NMR can be where you actually correlate the hydrogens, specific hydrogens to specific carbons or oxygens or whatever. And you can do really cool things with NMR. Can you imagine we as in not me, I was not part of that group, but the point is we as in bigger we can figure out the structure of a protein. Millions of amino acids in there using NMR. So it's really cool, but we are not doing that cool part. We're going to stick to the basic one-dimensional part. So at this level, to answer your question very, very simply, Gavin, the answer is, well, not just by that. We need to take all the clues and put them together.
Right. So not by integration, but all the 4 parts?
All 4 parts,
Okay, yeah.
exactly.
Okay, got it.
Exactly.
Cool.
For now. Okay, how many signals did this have, guys?
That one had.
How many signals?
3.
3, 4?
4. No, it's 4. No, you were right.
A, B,
I'm
B,
losing it, sorry.
A, C. Do you all agree?
Yes.
Thus, what's the integration ratio? And I just to keep things simple, I just go in the order. So let's start with A. How many hydrogens causing A?
6.
How about B?
4.
How about C?
1.
How about D?
3.
And can I reduce
No.
this further? That's your integration ratio. You're done. Does that sound okay? So are you guys able to do that for the others? Let's do one, at least maybe one more.
One
The
tricky
tricky
one.
one.
Oh, there you go. The trick.
How many signals did this guy have? 5?
5.
Do you all agree? How many signals?
It's on the page.
Remember, these were separate,
Yeah.
these were different, they're diastereotopic, right? Is that a yes?
Yes.
Okay, and then C, oh, I forgot that, okay. The C
Yeah.
and E, right? So what is the ratio? A to B to C to D to E, what is the integration ratio expected?
One to one to 2 to 3. No, to 1. Sorry, the last one's 1.
Everybody agrees? That's really it. Can I answer any questions? Of course, there are more examples which I encourage you to work on, but is there any question that I can help you understand better? Okay? So that's integration. What was the third thing?
Chemical environment.
Say this aloud, Anand.
Chemical environment.
Sorry, Eric, I'm not able to hear you.
Chemical environment.
Chemical environment, yes, absolutely. Meaning chemical shift. Where in the spectrum does a signal show up? So let's talk about that. I have again a few handouts for everybody, please, and they're floating around. If you don't have enough, that's because more went to a different part of the room. Please pass them around, make sure everybody has them. So let's look at how is an NMR spectrum set up. We saw IR yesterday. Let's look at the setup of an NMR spectrum. And that is chemical shift. Chemical shift has a symbol delta, lowercase delta. Its units are ppms, parts per million. There's a formula which we are not going to go over that uses the megahertz magnetic field strength and converts it into ppms. But the point is, we will only use ppm. Now, unlike IR, where the signals go down, here the signals go up. So these are actually peaks. Proton NMR spectrum, I lost my black. Proton NMR spectrum has a range of from 0 ppms to about 14. Very rare to see any proton signal going higher than 14 ppm. Very, very, extremely rare. Where is my black? Oh, there it is. Cool. Are you guys okay? Now, there are a few terms for us to get familiar with. Again, we're not getting into the depths of why and how. We're just learning these terms so we can use them. A, the higher the ppm value is, the higher the chemical shift value is. So going in this direction, we call this downfield. Relative to, this is a relative term, it's not an absolute term. So the higher the value, the more downfield it is, the smaller the value, the more upfield the signal is.
So inversely.
Relative to each other. So for example, again to understand this, let's say if I have two signals, there's one here, I'm going to call this B and I'm going to call this A. We can say A is more downfield compared to B. Or we can say B is more upfield compared to that. So these are comparative terms. We understand that, everybody? Another way that, and these are also comparative terms, the more downfield the signal is, the more de-shielded hydrogens are, meaning they have less electron density around them. So this is where electrons come up. Electron cloud that surrounds the nucleus creates like a shield around the nucleus and protects it from the external magnetic field. So the more electron density is pulled away, the more the nucleus can feel the magnetic field. The more electron cloud exists there, the more shielded the nucleus is from the external field. So the point is, the less electron density around the hydrogen or the nucleus, hydrogen, since we are talking about hydrogen, proton and NMR spectroscopy, we are focused on hydrogen. So the less electron density a hydrogen atom has around it, the more de-shielded it is, the more downfield the signal shows up, meaning higher ppm values. Opposite is for upfield. The more shielded by the electron cloud hydrogens are, meaning have higher electron density around them. So the more shielded a hydrogen atom is, the more upfield its signal will be, which is lower ppm value. So just some terms, if you hear those terms, just for you to understand, oh, downfield means higher ppm, upfield means lower ppm, blah, 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 blah. Are we all okay so far? No. Okay, cool. Can I erase this stuff?
Yeah.
Okay. Now, here's the thing, and this is all you will be doing in lab next quarter. First lab next quarter is NMR. How do we know where is zero? The instrument doesn't know. We have to tell the instrument this is zero, and then the rest relative to that. So how do we tell the instrument where is zero? We actually add something to our sample. We add a reference. And the reference compound used in NMR, no matter which NMR you do, the reference compound used in NMR is TMS. Stands for tetra methyl silane. What do you think silane is? What is silane referring to? Sorry?
Silicon.
Silicon, exactly. Where is silicon in
Silicane.
the periodic? Where is silicon in the periodic
16.
table?
No.
Just
no,
below carbon is.
Mm-hmm.
How many bonds does carbon want to make?
4.
So how many bonds do you think silicon wants to make?
4 bonds.
They're in the same family. So tetramethyl silane. What is that? It's silicon connected to 4 methyl groups. How many signals do you think TMS should show? Proton signals. Do you think TMS should show?
1 signal.
Because all 12 of the hydrogens are homotopic, totally identical. And because they're attached to silicon, which has a lower electronegativity than carbon, way lower electronegativity than carbon actually, this signal is, generally speaking, the most upfield possible. So that's why we add it. And you don't need too much, you need maybe 1 drop, maybe 2 drops. And then we tell the reader, okay, make that 0. All other signals, which are hydrogens or carbon or oxygen or nitrogen, will be downfield relative to it. Yes?
So, in an NMR machine, do you load like liquids or solids?
Solution.
Or solution.
Solids, no.
Okay.
They can be liquids, so if the compound is a liquid, best to run it neat.
Okay.
But if it's a solid compound, then we have to dissolve it. And that's my next point.
Okay,
Yeah,
okay,
go ahead,
yeah.
no, go ahead, finish.
I was just gonna ask, like, how does it not detect like water?
Good, it does.
Oh, it does. Okay,
It
just
does,
ignore the spike.
but that's why, good. That's why we don't use solvents with hydrogen. We use, so that's your reference, guys. The only purpose of TMS is to mark the 0 point, okay? But if you need to dissolve your compound in a solvent so we can create a homogeneous solution, then we have to use what does that mean? Deuterated solvent.
Well, something
What
like
is
saturated, but
So
no.
there's, no, not evaporated.
No, saturated.
No, not that.
Something
Saturated
contrary to.
Deuterium?
Exactly. Deuterium. What is deuterium?
H.
H2. Exactly, it's an isotope of hydrogen, H2. We represent it as D. H is proton, H with a mass number 1. D is mass number 2, D. So one of the common solvents you will use in lab, although any solvent can be deuterated and you can buy those, we don't have that big a budget, so we only stick to one, which is the most common one, and that is deuterated chloroform. Chloroform itself is CHCl3, but this H is replaced by deuterium. So, when you dissolve the compound in deuterated chloroform, basically what we are trying to do is not deal with the proton signal from the solvent. But is it possible to have some tiny concentration, maybe 0.5% or so of the protonated in the deuterated? Unfortunately, yeah. So we might see a solvent signal too. Now, chloroform typically shows up around 7.24, 7.3 parts per million. You might end up seeing a small signal which is really for protonated form, even though we use deuterated solvent, but again, contamination. Some solvents interact with moisture in the air, so they get protonated. So all of those things do happen. So yeah, I think that's where you were going.
Yeah, kind of.
So yeah, if there is a proton in the solvent, we will see signals. So you got to know where that is so you can eliminate it out.
So,
Yeah.
if you're using if you're using like a polar solid, with that,
You can have deuterated water,
oh yeah,
deuterated
that makes sense,
methanol,
yeah.
deuterated any. In fact, nowadays there's a huge variety of deuterated solvents for NMR.
So then, what's to stop us from, if it's an organic compound, just dissolving it in TMS?
I'm forming the answer in my head right now.
Don't worry.
So, couple of things that I can think of. This molecule, because silicon is low electronegativity compared to chlorine, which might cause the solubility of the compounds, organic compounds in this guy. That's my guess.
Right.
B, it's very volatile,
Okay.
extremely volatile. So it evaporates really quickly. So probably won't work for general compounds, won't work very well. C, more expensive than that.
Oh, that's, yeah.
When we buy that, we can buy a big bottle and keep it in the fridge. It's great because it's also somewhat volatile. Chloroform also evaporates reasonably quickly. So we can buy a big bottle and store it in the fridge so it's safe. This we buy in tiny bottles at a time and we make sure, please, one drop, just one drop, because yeah, it's way more expensive. So all of those factors come in. Anything else, guys? Yes?
Sorry,
No, don't be.
why is electronegativity pulling away from the silicon?
Silicon's electronegativity is lower than that of carbon.
Oh.
That's, I don't know the exact values. I don't memorize those, but that's basically. Carbon is more electronegative than silicon. Are we all okay? Does everybody understand the purpose of TMS?
Oh yeah.
Is that a yes? Okay, then let's do, oh shoot. Too many questions, Gavin. Sorry. I'm just okay, let's look at, I gave you guys that handout, right? With the, so
Yeah.
just look at the photon NMR part of it. Let me give you some ranges where to expect signals. And then I'll give you an actual table, just like we did for IR yesterday. One bottom line you will have to keep in mind in NMR, no matter what kind, a methyl, everything else being the same, methyl signal will be slightly lower ppm value than a methylene signal, lower than a methine signal. So just to give you an idea, everything else being the same. Just as an example, let's say for some compound, this guy shows up at 3.5 ppms. Everything else being the same, I can expect this one to maybe be about 3.7 ppm. I'm estimating here. a little bit more than that. And everything else being the same, I can expect this one to be even a bit higher than that, maybe 3.9, maybe 4, or so and so forth. So everything else being the same, methyl signals have a lower ppm compared to methylene, which have lower compared to methine. Sounds okay? Okay, let's look at the general regions here. Where do the signals generally show up in a proton NMR spectrum? Now, one of my favorite values here, by the way, in this you can start from right or left, it's totally up to you. It's not like IR. In this case, you can actually identify every single signal you see in NMR. So I love the 6.8 to 8 zone area in here. Then I find the 9 very helpful. And then I find the 10 very helpful, and then anything about 12, those are really helpful, and I'll tell you why in a second. And then over here, I really love the 3.5 value. 2.0 is very useful. 0 to maybe 1 to, so this is obviously not to scale, as you can tell. Why? 12 to 13, this is where the most de-shielded hydrogen shows up. And that is the hydrogen in a carboxylic acid. There is no other hydrogen that is more de-shielded, meaning electron density has been pulled away from the hydrogen than that. 10 is similar, but less so, because this is where phenol hydrogens show up. 9, again, very unique, because this is where aldehyde hydrogen shows up. I'm trying to highlight the hydrogen that shows there. Guys with me? 8 to 6.8 is very unique also, because only benzene hydrogens show up here. Depending on how many there are, you'll have signals in that range. 3.5 I love because when you have a single bond O shows up. And again, remember, methyl is less than methylene, less than methine, so it can go up till 4, 4.5, so on and so forth, but starting here, you can go higher depending on what kind of hydrogen that is. 2, this is where 2 kinds of hydrogens show up. Either the ones that are next to a ketone, or next to a benzene. The benzylic hydrogen. Oh, okay, I need to. Can I finish this? Because we can't draw all over again. I apologize. So really very clear places where they show up. Now, ordinary, plain old simple sp3 carbon hydrogen, the hydrogen, plain old simple alkane hydrogens show up in that range, 0 to, those are the most shielded hydrogens. Vinylic hydrogens, those are hydrogens on a carbon-carbon double bond on an alkene. The vinylic hydrogens can be anywhere from, again, these are approximate ranges, please remember that. This region is where vinylic hydrogens show up, meaning hydrogens that are on an alkene. So notice in proton NMR, benzene and vinylic are different ranges, although sometimes depending on other groups they may overlap a little bit, but they are expected to be different. Can you, oh, I didn't give you the table. I'm going to hand this out to you guys. Just like IR, please don't treat these as crutches, because last quarter when we do the ACS final, we will not, no, I have a couple more values to put on it, guys, I apologize. I promise, just a couple more. Please, can you pass? I actually forgot where one of them should be, so that's why I need to look it up.
What?
Oh, yes.
Oh,
Between 2.3 and 3.0. So, somewhere in this area, we can see an alkyne hydrogen in that area. And last two, which are not here yet, OH, alcohol OH, and amine NH. Their values, they have a really big range. Their values can be anywhere in this range. Alcohol OH or amine NH can be anywhere in there. But the good part is they are generally broad, generally speaking, because of hydrogen bonding, and generally speaking, actually maybe I won't use that, because generally speaking they don't show multiplicity because of hydrogen bonding. So once again, I would urge you to use the table now, but get to a point where you can just imagine this in your head and say, okay, yes, an ether H shows up here, benzene shows up here, carboxylic acid here, so on and so forth. So we are not tied to the table. Okay, so that is chemical shift. Today is Wednesday, right?
Yeah.
Monday we have class? Yes, we do.
Yeah.
But no quiz, right?
Oh,
Because we have an
the
exam.
next
Yeah.
one,
So no, okay, then we'll just continue on Monday with